just let us recap what we have done on Monday. We were talking about the measurement of dispersion, and we said we either have a population or we have a sample. And in a way, we hope that the sample represents the whole population. And we said population is characterized by parameters. And these parameters are usually abbreviated with Greek letters, whereas a sample is defined by what is called the statistics. And they are usually normal letters. So for a population, we can have the mean, which in the sample is abbreviated with this X bar. We said we can have the variance, and in a population, excuse me, this would be usually abbreviated with sigma square, whereas in a sample it would be S square. Or, if we don't like the squares, we can also have the standard deviation. Where we have S here for the sample and sigma for the population. And I showed you how we can measure these variance and standard deviation. For the variance, we said what we do is we measure each of the data points that we have, bless you, minus the mean. We square that. We add all our differences up, and we divide by the number of data points that we have. So that's the variance. For a sample, we said in principle, we do the same. So we take all our data points, we subtract the mean, and square the whole thing, sum up all the data, and divide this time by n minus 1. So if we have, say, a sample of 20, here we would divide by 20, whereas here we would divide by 20 minus 1, i.e. 19. And these are our variances. And of course, the standard deviations, that would be simply the square roots of these variances. It's pretty much straightforward, I guess. And I would not hesitate to ask you in, say, the summer exam to calculate the standard deviation of a sample that has 4 or 5 data points. Yeah? I would not do that for 120 because there's no point in doing that. You would get it wrong anyway. I would get it wrong. And we have computer programs to do that, so why should you do that? Anyway, that was just what we have done on Monday. What I want to do with you today is a little bit talk about frequencies and distributions. And I think a very easy way to illustrate what I mean by that is if I show you an example from actually what you have done. Let me quickly go to here. This is actually the results of your recent homework. We have what is called a histogram of the grades that you achieved. And it is, if you like, it is a distribution of the grades that you got. And it also shows here the number of the submissions and the points scored. And that is a very typical figure for such a histogram. Now, what does this tell me? I can read quite a lot from this histogram. It shows me that there were quite a number of submissions. So it is really not terribly, in a way, it is fairly fine-grained. I have a lot of details here. And I can see, for example, here this number that is roughly, well, that obviously is the top, the highest number of submissions, and people got 19 out of 20, which is pretty good. So I can, from a histogram like that, very easily read off how many people got good grades. Can also see that there are a number of people who are struggling. So, for example, this one here is really interesting. It was 0, and very clearly something went wrong here. Bless you. So if you see something like that, and luckily it's only, I think it was 1 or 2 people. So I had to go back to the submissions and had a look at that. What is going wrong? It turned out that one person just simply put their name in and left everything else empty. Well, the program thought, okay, fine, can't do it, so everything is 0. Probably just a nervous finger and, pressed the submit button too early. The other person did all the questions. Now, if you remember, it was 20 questions and you had 5 options per question. So, if you did it completely blind, if you had no clue about statistics, and you just did the questions random. Oh, well, today's Thursday, why don't we put B for question 3 or something like that? Then you would have an expectation, and we're talking about expectations in another lecture, then you would have the expectation that this person gets at least 4 questions right. From the fact that this person got 0 right, this tells me that this person is overthinking things. They probably know a little bit about statistics, about pH and molarity, but they make it far too complicated and then they doubt themselves. So this is what this histogram tells me. Now, how would I be able to find out just from this histogram, how many people have submitted? How would I do that? Any ideas? Absolutely. I simply sum up all these submissions. So here I have 2, here I have 2, here I have 2, here I probably have 4. So I can tell, for example, that a certain number of students have 10 or less. So just simply by summing up all these submissions, all these frequency data. And this number of submission, that is actually called frequency. It basically tells me how often this grade was achieved. It's interesting, this guy here. Not many people, well, a decent number, but not too many people got all 20 right. Having had a look at it, the killer for you was the question about the pH of a 1 nanomolar hydrochloric acid, which I was very pleased. What would be the correct pH? What is the pH of a 1 nanomolar hydrochloric acid? 7. If people put in 9, and we had this discussion before, if people put in 9, there's something wrong. Because if I have an acid, the pH should be 7 or lower, at least. Yeah? But pH of 9 is higher than that. So you're contradicting yourself. Yeah? I've made videos to all the questions, or videos of model answers, so please have a look at these model answers. And if you still have problems, then just let me know. So this is the distribution of the grades. So this is a typical distribution. It shows me how grades are distributed amongst students. I can't, of course, at this point I can't identify who, for example, was this one here, or from the histogram I can't identify who got everything right. But in a way, I'm not too keen anyway. I can identify people because I've got the submissions, but the histogram doesn't tell me that. But really, do I need to know that? Not necessarily. What this histogram also, it shows me further, gives me further information. It shows me that a lot of people really can do that stuff. So everybody who has more than, who has 14 or more questions right would get a first-class degree. Yeah, because that is 70%. Obviously, people in that range here, they wouldn't get a first-class degree. I all want you to get first, so that also indicates to me that I need to work with these people there. And then it becomes interesting to identify them. Now, what I can do is really, I can sort of, I don't like these boxes that you frequently see in a histogram. So what I can do is I can connect, in a way, the middle points of each of this box. And I can do a line. So this here would be my distribution line. Not pretty, but you know what I mean. I notice that there is a peak here at 19, and there is a sort of a tail. That here is the tail here in this direction. Let me draw this distribution again, very schematically. So here's the frequency, and here are the grades. And what it pretty much looks like is something like that. Now, this is, I would say, a rather unusual distribution. If you did, for example, an essay, and I was marking an essay, what I would usually find, so here we have the frequency, and usually it is abbreviated just with an F, and grades. What I would usually find is that there are really only a few people who bomb out completely in an essay. Didn't get the question right or something like that. Most people would be around the, say, the 2-1 mark. Here that would be first, 2-2, third, and here would be probably fail. And this obviously is a very different distribution. So that would be for an essay compared to this weird distribution that I have here. If I make the test too hard, what would I get? I would get probably a lot of people failing, and only a few people getting good grades. What you see here is what is called the skewness of a distribution. And I want to point out that there is no R, no letter R in the word skew. It just simply means it is not like this one here, where we have both sides nicely symmetrical. So here that would be symmetrically. Here, not symmetrically. Here, not symmetrically. And because this tail here, this is called the tail, because this tail points towards the positive direction, we say this distribution curve is positively skewed. And of course, there's no skew in that, or hardly any skew in that. On this one here, it points in the negative direction, so this would have a negative skew. Are skews bad? Are they bad?
Not necessarily.
Why not?
Because that shows a decent distribution, doesn't it?
This one here, this would be exactly what I wanted. I really want only a couple of people not doing well. Well, I don't want anyone to do not well. Wait a moment. I do not want anybody not to do. Oh yeah, that's a double negative, so yeah. I want to do everybody well, so I want actually I want everybody. What did I say? Oh, it's too early. So I want everybody to be here and hardly anyone negatively skewed. Yeah? Now, what I've shown you here is a curve that happens very, very often when we do experiments, when we do measurements, when we do anything. And this obviously, it's not an essay curve. This thing is called a normal distribution. Normal distribution. So, if we have something like that with a frequency, it looks a little bit like that. It looks like a nice bell, if you like. It's also called a bell curve. So, for example, if I measure the weight of mice, and I have a large enough sample, loads of mice, what I will find is that the weight is probably normal distributed. It shows something like that. There's actually an equation for that, but I can't remember it, and it's fairly complicated, so I thought, there's no point in me showing you that. A, I have to look it up, and B, you forget it immediately, so no point. But this is a normal distribution curve. But it's not just any bell curve that you could draw. The characteristic of a normal distribution is that here it is symmetric. So, symmetric. And this point here this would be actually the mean. Symmetric around the mean. If we are looking at a population, we could say this is the mean. If we are looking at a sample, at a very big sample, and it needs to be a big sample, we would look at the X bar for the mean. It also has a few more features. From the mathematical expression, which I'm not going to bother you with, we know, and I try to draw this as accurate as possible, we can define a range. Well, let me do that in a different color. And we can say, if we go one standard, let me put it here, one standard deviation, if we're talking about a population, each side of the mean, so this here would be plus the mean, or mean minus 1 standard deviation, that's this one, and that's this one here. If we define this range, we will find that roughly 68% of our grades, of our data, 68% of our data will sit in this range. We can even go further, and we can say, right, what would happen if we go 2 standard deviations? So that would be 2 standard deviations. And here 2 standard deviations. What happens if we do 2 standard deviations, left and right from the mean? So that's the green part here. And we know from the maths that this would give us roughly 95% of the data. So 95% of the data for a normal distribution are within plus minus 2 standard deviations of the mean. And we can do another one. We can do 3 standard deviations. Now it gets really colorful. I do that like this. And we know that 3 standard deviations capture 99 point, what was it? Yep, 99.7% of the data. Almost all the data, but not 100%, 99.7% of the data. And this is what is generally known as a sort of rule of thumb. It's the 68, 95, 99.7% rule. And I want you to, in a way, remember these numbers. 68, 95, 99.7. What can you do with that? What does this tell us? Let's draw our lovely normal distribution. This is an essay. This is an essay which forms, which is done by people, by students, so essay marks, essay grades. Let's say we have a mean here, and this is all the students. So this would be a population. All the students in one cohort, and this would be, say, 65. Now tell me, how many students got less than 65%? How many students got less than 65%? 50%. How? Why? You're absolutely right, but how did you do that? Because it's symmetrical. So, I know that this is 50%. And, of course, this is 50%. Because otherwise it wouldn't be symmetrical. So, 50% of the students have less than 65%, and 50% have more than 65%. Okay? Happy with that? Now, of course, I can go further. Frequency grades. $65. And when I did the calculation, I noticed that the standard deviation of that, and we discussed how we can calculate the standard deviation. We can calculate, I calculated the standard deviation. The standard deviation in this case is 10. Now, I want to know where in my curve would be the point here and here, where would be where would be the mean plus one standard deviation? It's very simple. It would be 75 here. And on this side, on the other side? 55. That is plus one standard deviation of the mean and mean minus one standard deviation. I want to know now how many students are between 55 and 75. How many students are between 55 and 75? 68. This is my 68%. I can even now go further and say, okay, let's go for another standard deviation. That would be 45 and 85. And I can ask a question, how many students would be between 45 and 85%? That would be 95%. So most students would be between 45 and 85%. Yeah? This is what the standard deviation can do. This is what the normal curve can do for you. Now, I want to give all students let me draw that again. $65, $75, $85. Here was 55, 45. Now, all students, I want to give all students who performed better than 75. Everybody who is better than 75, I promise they will win a prize. How many students are doing better than 75 in percent? Any ideas? 32? How did you get that? 100% minus 68. It's an interesting approach. Why don't we just simply add up what we have? First of all, how many students did worse than 65%? How many? 50%. So we can disregard this 50% already. Yeah? Now we have this bit here to deal with. I make it green. Can we calculate how big this bit is? It is? Who said that? 34. Why? Ah, very good, yes. We know that both parts here, this captures 68%. Yeah? This one and this one together, that's one standard deviation away from the mean. This is 68%. So half of it, because it's symmetrical, this would be 34%. So this bit here, that would be 34%. So all I need to do now is add these things up, and I have 50 plus 34% gives me 84% that are in this range here. Yeah? Or in other words, only 100 minus 84 are in this range here. And that would be 16%. 16% of students are doing better than 75%. Got it? Shall we do another example? Frequency. $65, $75, $85, $55, $45. I want to know how many students are worse than 45%. How many students do worse than 45%? So it's basically this bit here. How do I do that? Again, we just simply calculate the other way round. We calculate how many students are better than 45%. So, how many students are better than 65? How many are better than 65? 50%. Now we can also calculate this bit here. How big is this bit, this bracket? Well, we know, because it is symmetrical, again, that here, to the 2 standard deviations, this bit here, it would be 2 standard deviations. That was 1, and so that is 1 standard deviation. That is the other standard deviation. We would know that this together is, what was it? 95%. And therefore, this bit here would be 95, half of 95, because this is only this bit. And this one here is the other bit, the other half, because it's symmetrical. So that would be 47.5%. And now I add them both together. I have 50% plus 47.5%. And that gives me 97.5%. So I know that 97.5% are doing better than my cutoff point. So therefore, this cutoff point is 100 minus 97.5. That gives me 2.5%. Only 2.5% are doing worse than 45%, than my cutoff. Does that make sense? Actually, it's quite interesting, because anyone thinking about going to medical school? Hands up. Poor souls. The thing with medical school is you have to do this entrance exams. And in these entrance exams, usually the marks, the grades, follow a normal distribution. And then every school who does these entrance exams says, we only take people in the top category, and they define what the top category is. Some of them say, right, you have to be, in your personal mark, you have to be better than, say, 97.5% of all the other students. So you would have to be at least 2 standard deviations away. This is how they actually define their cutoff point. By looking at that and saying, right, we have only that many places, so our cutoff point, and it changes every year. It changes. They vary the cutoff point. Now, there is a way you can calculate your personal mark. So far, we have only spoken about how many students are below say 45%. How many students are better than, say, 75 here in a grade, and so on. And you, as an individual, have no sort of, you don't know really where you stand. But you can calculate with a very simple equation, you can calculate where you are in this point, in this curve. You can calculate how many standard deviations you are away from the mean. And this equation for your personal, for your individual grade, so individual grade, this is also known as the set score. And how do you find your individual set score? Let's assume you scored X percent. So set equals X. You just simply subtract the mean and you divide by the standard deviation. That would be your set score. Let's have a look what this looks like in practice. Let's assume you scored 50%. That was your score. Respectable, I would say. It's not too bad. The mean, however, was 65%, and the standard deviation was 10. How far away are you in terms of standard deviations, in terms of your personal set score? How far away are you from the mean? Well, we have 50 minus 65 divided by 10. That is your set score. This would be 50 minus 65 minus 15 divided by 10. That gives us minus 1.5. So, a set score of minus 1.5 tells me you are 1.5 standard deviations away from the mean, and the minus tells me you are on the wrong side of the mean. You are doing worse than the mean. So what I'm probably going to do, if I've got time over the weekend, I will look at your submissions for the PH homework, or I might even, I could do that. I can email everybody the mean grade and the standard deviation, and you can all calculate your individual set score. And then on Monday we see how many people are negative and how many people are positive. Right? Have a lovely weekend. Don't forget to submit your revisions, your revision homework, deadline Monday midnight. Have a good weekend.